As we begin to learn solving equations, we're going to begin by solving equations using addition and subtraction. To solve an equation means that you find the solution of the equation. And again, the solution is the value of the variable. Once you isolate the variable, which means to get the variable by itself on one side of the equation, then you have found the solution. Here's an example of what isolated variables look like and what they don't look like. If you had the equation x equals 8 minus 5, well, x is by itself on that side of the equation, so it's isolated. If you have 7 minus 4 equals y, y is isolated. It is by itself on this side of the equation. The equal sign breaks up your equation into one side and another, just in case you were confused. These variables are not isolated. You can see that x plus 5 is on one side of the equation and 8 is on the other. X is not by itself. It's being added to 5 here, so it's not isolated. So at this point, you would not have the solution to the equation. Here as well, 4 plus y. Y is not by itself. Y is not isolated. So we're going to begin with one of two properties in today's notes. And the first one is the addition property of equality. And the addition property of equality states that the same value can be added to both sides of an equation and it will still be equal. So if I had this equation to begin with, 2 plus 3 equals 5. Let's say I could add anything to both sides and I would maintain equality. I kept it really simple here. I didn't get this number from 2 plus 3 equals 5. I just chose a very simple number and I said, well, I'm going to take it and add it to both sides. So I added 1 to both sides, just because the addition property of equality says I can. And does it work? I mean, I'm showing you that it does. 2 plus 3, now plus 1, equals 5 plus 1. And this is true because if I add both sides up, both expressions, I get 6 equals 6. So I've maintained the equality. Algebraically, we can make generalizations with variables and represent this property. If I begin with x equals y, well, if I add the same thing to both sides, let's say z, for example, then I end up with x plus z equals y plus z. And that is true because x and y were equal to begin with. So to solve an equation by isolating the variable and using this property of equality, we use inverse operations. Now, addition and subtraction are inverse operations. They undo each other. So, for example, if 2 plus 5 equals 7, well, the inverse of that, we could say, is 7 minus 5, and you get right back to 2. So, here's our first example of solving an equation using inverse operations. I have x minus 8 equals 17. Well, I can see that I have a minus 8 going on here. The opposite of subtraction is addition. The inverse operation of subtraction is addition. So I can say I can add 8 to both sides because of my addition property of equality, and I will still have an equal equation. It will still be balanced on both sides. So if I take this and do so, and then I do the calculations, negative 8 or minus 8 plus 8 is going to be 0. And 17 plus 8 is 25. So I'm left with x plus 0 equals 25. Because of the additive identity, meaning anything plus 0 is itself, then I can say that x equals 25. X is now isolated. 25 is my solution. Now, if I wanted to check to see if it was correct, I could substitute. And when I say substitute, I mean take what you got, which is 25, and you plug it back into the original equation. So it will look like this. Is it true that 25 minus 8 equals 17? And you can put that little question mark just to see. Calculate 25 minus 8, and you're going to get 17 equals 17. And that's a way to self-check to see that you are in fact correct. So here are some examples of solving equations using addition. If I look at 24 equals b minus 7, I see that I'm subtracting 7 from my variable. I want to get my variable by itself, so I need to isolate it, get it by itself. And the opposite of subtraction is addition. So I know I can get b by itself by adding 7 to both sides. Remember, what you do to one side, you must do to the other. Negative 7 plus 7, and I know that you may be confused saying, well, isn't that minus 7? Remember that it's also plus a negative 7 because we can make that change with subtraction. So negative 7 plus 7 is just 0. So you end up with b plus 0, technically, equals 24 plus 7, which is 31. And I can say that because of this additive identity, 31 equals b. Now, I'm not always going to bring down that plus 0. You're going to understand that I've done that inverse operation in order to get 0 with addition and subtraction properties. So that's going to just be implied. And so I am going to cross them out. Okay? They don't necessarily cancel each other. That's inappropriate language to use, but it is important to know that you have added the opposite in order to get to one of those identities, so you have just the variable by itself. If we come down to example B, I have negative 14 plus C equals 11. And you're thinking, I thought we were doing addition. This is addition, and I know the opposite of addition is subtraction, so I'm really confused here. But what's important is that the sign in front of the term is what belongs to it. So you have to do the inverse of the number that you intend to move. So if you want to get C by itself, meaning you want negative 14 to get the heck out of there, you need to do the inverse operation of negative 14. As weird as that sounds, if you take negative 14, what can you do to it to make this C plus 0? Well, you have to add 14. And when you do it to one side, you must do it to the other. Now, negative 14 plus 14 is 0. So you're left with C. And then 11 plus 14 is 25. And if you wanted to check, you could plug 25 right in here, and you're going to see that negative 14 plus 25 does in fact come out as 11. In example C, x minus 8 equals 0. Well, the opposite of subtraction is addition, so I'm going to add 8 to both sides. So then x equals 8. And does that make sense? Does 8 minus 8 equal 0? Of course it does. And then example D, 3/4 equals y minus 5/6. And we haven't done work with fractions yet, but who says that we can't follow the same directions? Well, we can. So this is y minus 5/6. And the opposite of subtraction is addition. Okay, so we're going to say, well, I can add 5/6 to both sides. And I'm adding the opposite here, so I know that that is going to be a sum of 0, leaving me with y on this side, but I might have to do a little extra work here, aren't I? That's okay. So 3/4 plus 5/6. I'm thinking common denominator, that common denominator, 8, 12. It's going to be 12. So I'm just going to rewrite this with a denominator of 12, keeping in mind that I'm adding, okay? 4 times 3 was 12, so I'm actually multiplying by 3/3. 3 times 3 is 9. And then what did I do to 6 to get 12? Well, that was times 2. So I'm actually multiplying by 2 over 2, which is actually just 1. 6 times 2 is 12. 5 times 2 is 10. Now I can add these. Just kind of leave this alone because I've rewritten the fraction problem. And 9/12 plus 10/12 is 19/12. 19/12 is actually simplified, and so for the purpose of this, I'm going to just leave it. Y equals 19/12. And does that make sense? I mean, something minus 5/6 equals a number that's less than 1. So this is greater than 1, right? Because it's 19/12, it's more than 1 whole. So that solution, it makes sense to me. So I'm okay with it. Next up is the subtraction property of equality, which is extremely similar to the addition property of equality. It states that the same value can be subtracted from both sides of an equation and it will still be equal. So again, if I have something like 4 plus 7 equals 11, I can subtract the same number, any number really, from both sides, and I will still have an equivalent equation. It'll be equal on both sides, balanced. So If I subtract 3 from both sides, let's say I take it from the 7, and then from 11, I have 4 plus 4 equals 8, and 8 does equal 8, so I've maintained that equality. Algebraically, you can represent the subtraction property of equality by saying, well, if x equals y, if I subtract z from both sides, then x minus z equals y minus z. So we're still going to use inverse operations to solve, only we're going to be saying the opposite of addition is subtraction. They are interchangeable, works both ways. So a plus 5 equals 11. In order to get a by itself, the opposite of addition is subtraction. So I will subtract 5 from both sides. This does get me to a plus 0 equals 6, and because of that additive identity, I have a equals 6. Again, you can substitute to check. If I got 6, can I say that 6 plus 5 equals 11? Yes, I can. I know I'm correct. So here are some examples using subtraction to solve. T plus 14 equals 29. The opposite of addition is subtraction. Subtract 14 from both sides. That gives me t. Remember, this equals 0. T equals, I can subtract, that's 5, 15. Okay. How about 10 equals x plus 35? Opposite of addition is subtraction. So that means I have to subtract 35 from both sides. 35 minus 35 is 0, leaving me with x on the right. I have 10 minus 35 here. What the heck's that about? Well, I can do that, right? I'm just going to get into a negative amount. 10 minus 35 can be thought of as 10 plus a negative 35. That's supposed to be negative. And then signs are different. Find the difference. I have 35 minus 10 in my head. I know that's 25. Sign of the larger number in absolute value is negative, so this is going to be negative 25. Some of you may have been able to do that in your head, and that's awesome. 10 minus 35, well, that's negative 25. That's exactly right. How about an example like this? 76 hundredths equals 34 hundredths plus b. Opposite of addition is subtraction. Subtract 34 hundredths from both sides. Sometimes it's going to work out really nicely for you, leaving you with b equals 6 minus 4 is 2, 7 minus 3 is 4. Bring my decimal point down. We're good. 42 hundredths equals b. And then we have example D. And example D is very special because I have negative 5 equals 7 minus x. Now you're saying the opposite of subtraction is addition. So I'm just going to add 7 to both sides. Well, is 7 negative? If I add 7 to both sides, let's see what happens. If I add 7 and add 7, what's 7 plus 7? I need it to be 0. It's 14. So that actually can't work. So remember, you need to consider the sign of the number you're moving. And the opposite of a positive is a negative. And so I need to actually subtract 7 from both sides. That's absolutely okay. As long as what you do to one side, you do to the other, you will maintain the equality. And if you make a mistake, you can always fix it. It's the best part about equations. 7 minus 7 is 0. And negative 5 minus 7, that's negative 12, equals. Does that equal x? Have I used this yet? I have not. This is negative x. And this is where we get into a bit of a misconception. If negative 12 equals negative x, then that means, now think about it with me here, if negative 12 equals negative x, then positive 12 equals positive x. And we're not interested in negative x. We want to know what x equals. Well, if negative x is negative 12, then x equals 12. Love it. And now, just so I can make it a little bit more challenging for you, I've mixed up addition and subtraction in 4 examples, so you'll be well prepared. If e minus 35 is 59, the opposite of subtraction is addition. So we're going to add 35 to both sides. This leaves me with e equals 9 plus 5 is 14, 5, 6, 7, 8, 9. E equals 94. If you weren't sure, take this, plug it in for e, say 94 minus 35 equals 59, and you have got the right answer. Example B, 651 plus c equals 800. This is positive, And so the opposite of that would be negative, meaning I'm going to subtract from both sides. Minus 651, this will leave me with a positive c, which is what I need. Minus 651 from both sides, that leaves me with 0 plus c, which is c. And then I do have to borrow, that's 7, that's 9. 10 minus 1 is 9. 9 minus 5 is 4, and 7 minus 6 is 1. C equals 149. If you're not sure, plug it in, see if you get 800, and you should. In example C, negative 105 equals A plus 110. Well, the opposite of addition is subtraction, so I will subtract 110 from both sides. This leaves me with A on the right. Negative minus a positive, well, I can say I'm going to add the opposite. Okay? Now I have negative 105 plus a negative 110. Signs are the same. Add, keep the sign. So that's 5, 1, 2, negative 215 equals A. And then lastly, example D. I have 12 equals negative 4 minus F. Well, remember, I work with the sign in front of the number I want to move. I want to get F by itself, and I know it's negative, and that's okay. I'm going to add 4 to both sides first, just to get that F by itself. And so 12 plus 4 is 16, and 16 equals negative F. Well, you know something that I can do, and I'm going to show you this right now. I can actually add F to both sides. When I do that, what am I left with over here? 0. And what's over here? 16 plus F. If 16 plus F equals 0, how can I get to what F equals? I can subtract 16 from both sides. Now, you didn't have to take this step if you understand what we talked about in the last board. But now you're left with F equals negative 16. We knew that 16 equals negative F, so F equals negative 16. But here you can see that I can move things around my equation still to prove it. So F equals negative 16.